So what I've drawn here my circuit, haven't I? I've got a resistor, which is where I'm going to convert my chemical energy to the energy, like light or heat or sound or whatever. I have a switch here. Now, what's the signs for the way I've drawn my battery?
Negative, positive.
Which one?
Positive's that one, and that one's negative.
Okay, so this is negative and this is positive. What's this?
A switch.
I've labelled the resistor. Now, which direction, clockwise or anti-clockwise, would electrons travel?
No, clockwise. I can't.
Clockwise for my electrons.
The current, however, is indeed going anti-clockwise.
Good stuff, Brio.
Wonderful. All right, now we do also need to know how we can measure what's going on in this circuit. And there are two pieces of equipment that we use to do this. The ammeter, it measures current in amperes. And an ammeter has very low internal resistance. Now, we can also think of the wires here are going around my circuit. They're like a highway. That's pretty easy for the electrons to travel along the wires. And we can think of the resistor, it could be like a dirt road or a bumpy road. Okay? It's harder for the electrons to travel through the resistor. Now, the ammeter is probably even a better pathway than the wires in the circuit. And so that's why they have very low internal resistance. So the electrons can travel through the ammeter with ease. And this is why the ammeter goes in the circuit. And I can represent that as a circle with an A in it for the ammeter. Now, if we think about what's going to make the pathway harder for the electrons, and a narrow wire is going to be more of a problem than a wide wire. If there's a wide wire, it's going to be really easy for electrons to find a way to get through pretty quickly. And so we can, our ammeter's wire is probably going to be a larger diameter than the wire of the circuit. Mandy's making some dry ice. Now, our other piece of equipment that we need to use to be able to make measurements in our circuit is called the voltmeter. And it's a circle with a V in it. It has very high internal resistance. And we don't want the electrons really going through that way at all. We want them to, we're going to discourage the electrons from going through it so that I can measure what's happening wherever it is that I attach the voltmeter to the circuit. And what might happen is like this. I can't put the voltmeter into the circuit like I did the ammeter because its internal resistance would be so high it's not actually going to work. So what we have called this, when I put it in like this is called in series. It's in series with the rest of the circuit. And you can think of this as, just say all the things were holding hands. Well, with our ammeter, it holds hands like in a circle, right? But with the battery and the resistor and all the wires are joined in a circle. But for my voltmeter, this is wired in parallel. If you're not sure how to spell parallel, the double is the L's, and they make like parallel lines. And so you can see here, what I've sort of, the reason why it's called in parallel is that this is sort of parallel to that. It's definitely not in series, because in series would mean that it has to be able to hold hands in a circle, and it's not holding hands in a circle, it's on the outside of the circuit. And the voltmeter measures potential difference. Which we call volts. It's really, this is probably, most of what you would need to do for a circuit diagram and understanding what's going on in a circuit diagram and how you would need to label it. So, you might also call this one a battery, etc. And you might label this as the conducting wire. This has got all of the features in our circuits that we need to be able to do for our current electricity circuit diagram. We do need to know how we're going to wire these into our circuits, ammeter in series and voltmeter in parallel. If you look at the bottom of page 31, we've also introducing a little bit of an idea here about current. And I was talking to you before about the movement of charge. Current is the movement of charge. But more specifically, current is a movement of charge per unit time. So Q is the symbol there for charge, and T is time. And our I is current. And it's measured in amperes, which are frequently shortened to amps. This is on your formula sheet. And I think on your formula sheet, it might be in the format of Q equals IT. Yeah, I'm going to say that can't be right. So that's the format that it is on your formula sheets. Okay, that's good. So what it's saying is the current, which is the movement of charge. If I want to measure it, then I'm going to stick a magnifying glass over a certain portion of the circuit, and I'm going to count how many electrons move per unit time. That's what the current is. How many charges move per second. And in actual fact, amps are a very large unit. And if you read this section here, a charge on an electron is 1.6 times 10 to the minus 19 coulombs. So charge is measured in coulombs. And the reason why we have some random names for our units in electricity is that they're named after the scientists who are working in this area. So the more normal way of thinking about it is, well, what's the charge? 1 coulomb is the charge carried by 6.25 times 10 to the 18 electrons. So that's a lot of electrons. Yeah, and our time is in seconds. So that's something that we're more familiar with. We often use milliamps because current kills. You don't need a lot of current to kill, and as Jared was talking quite rightly before, it's the current, where if the current's high enough, it can contract the muscles in your hand so you can't let go of the wire that's currently electrocuting you. That's why we often talk in terms of milliamps. You need to know milliamps and microamps as well. So if you look on the bottom corner of the page, you can see that the milliamp has got the little M in front, and then the microamp has got the micro sign in front. So this is another place where an examiner might be able to bring in these different units to see how well you handle really big or really small numbers. Or if you turn the page to page 32, we've got a simple circuit. It's got a power supply, a cell, it's got the ammeter, and it's got a resistor. We can use this equation here to determine the current flow. It says that we've got 0.8 coulombs of charge passing a point in the wire in 2 seconds. So that means that I equals 0.8 divided by 2, which is going to be for some reason in the booklet it's doubled it, it's multiplied by 2 instead of divide, so just put a line through it and it's definitely 0.4 amps. The self-starter of a motor car uses a current of 20 amps for 10 seconds. What quantity of charge flows through the starter? Well, in this case, we have been given that the amps are 20 amps and time is 10 seconds, and we want to find Q. So Q equals IT. Q will equal 20 times 10. So Q equals 200 coulombs. And we use the symbol C for coulombs. A scientific calculator draws a current of 15 milliamps. So here I is equal to 15 milliamps, and which is 15 divided by 1,000 amps. We have to calculate in amps, and we have to calculate our time in seconds. And if it has a charge flowing through it of 12 coulombs, then how long did the student have their calculator on for? We're calculating the time. Well, the time is going to equal the charge divided by the current. Which is then equal to 800 seconds. So we've gone through a little bit of an example using our first equation in